of the Moroccan Center of Game Theory. I guess everybody try to check what is the Game Theory Center. So it's started 1 year ago when I went to Morocco, and I tried to build a center between computer science, economics, and mathematics to develop mathematics. So it's, you can say it's more in applied mathematics. And I wanted this first winter school to be a combination between three fields, a topic which is the intersection between all these fields. And I have the pleasure to have a friend. There's an outline where he's in this intersection exactly. So I asked him, which topic do you suggest for this first year? And he suggested data economics. So we wanted the event to be international students. So that's why we have coming from. Yeah, thank you very much. So we have third of our participants coming from the international community, 10 countries: US, UK, Chile, Greece, France, and many others. Mali. We have also, and we wanted these people to connect with our PhD students. So actually in the PhD program, in Morocco, the PhD program is 4 years. In the center, the first year is a very intense training in mathematics and game theory. We have 5 candidates this year. It will increase. And this winter school will be also the occasion for them to learn about new topics, but also to connect with international students. And also with international students to know about Morocco. I guess many of you have never been in Africa. So perhaps it's your first time in Africa. And maybe you are surprised by Morocco. Many people, when they come, they are really surprised because they expect something completely different. So Rabat is very specific city in Morocco. It's like California, I would say, in terms of weather. The temperature all the year is good. you can surf. So our organizers and speakers were surfing yesterday, for example, just close to the Medina in Udaya. So I hope you will stay more than the duration of this event, and you can visit Morocco. If you need any advice, I'm sure that the group to which you belong, so each of you is assigned to a group with one local who can advise you. You have also Iman and Fatim Zahra. I don't know if they're in the room. So they are really amazing. So they are the project managers, officers of our center. And they are assisting me in organizing this event locally. And they did a very difficult and amazing job to make sure that everything went well for everybody, and you can have your transfer, you have your room. And given the number of people, it's not an easy task. Okay? So I'm not going to take too much time. We have all the week to discuss. Don't hesitate to talk to me, talk to Jason, to all of us, to ask questions about Morocco, the center, postdoc opportunities, hiring opportunities. We're going to hire, but not too much. 10 people, and the salaries are twice Europe, so you can compute. And I let the floor to Jason.
Thanks, Rita. It's wonderful to be back in Morocco again. I came here last year for the kickoff of this remarkable project that Rita is the director of, the Moroccan Center for Game Theory. And I'm super excited about the hard work that Rita's putting in to build a game theory center here in Rabat, Morocco, and to be a part of making it exceptional. So today we'll be kicking off the Winter School on Data Economics. I'm delighted to introduce Nicole Immorlica, who's a longtime colleague of mine. We started at Northwestern as junior faculty together in 2008. And since then, we've had just a wonderful collaboration and being part of things that Nicole's doing, and for many decades now. So she, for a number of years recently, was the chair of the ACM SIG Ecom, overseeing many hugely impactful and influential programs, making a wonderful community between computer science and economics and game theory. And so an exceptional person to be here at the first winter school of the Game Theory Center. So with that, I'd like to welcome Nicole Immorlica.
I think it's going to be a little hard to hold a mic and lecture. Are we recording this? It's like I have to use the mic because we're recording this, or?
I think it's good to use the mic.
Okay. Yeah, maybe.
And you have the button.
Okay.
So we are going to do the old fashion, which is
Right. I will try to hold a mic and write on a blackboard and look at my notes. Okay, so today my lecture is about machine learning, algorithms, and economics, and this is the first lecture of the school. I'm going to do some very sort of introductory level discussions and of first bandit algorithms and machine learning algorithms, and then I'm going to talk about how they interplay with economics. So in particular, I'm going to talk about online learning first. And then the online learning setting, we have two different sort of assumptions that we can use. One is that there's full feedback for the online learning algorithm. So that'll be the first quarter of the lecture, the first half before the break. Then I'm going to talk about learning with partial feedback. And that's going to be the second quarter of the course, or of the lecture, so the second part before the break. Then we'll have a nice half-hour break with maybe some delicious Moroccan treats, I hope, and some coffee. And then when we come back, I'll get into the more, so this is sort of your basic machine learning course. Then I'm going to get into leveraging this stuff in an economic setting. So then I'm going to talk about bandits and games. And here we'll see how all of these data-driven learning algorithms can be leveraged by players and games to reach outcomes that economists have hypothesized for, since the beginning of economics, since the 50s or something. And we'll see that these algorithms that we're developing in the first part can be used by players and games to reach these sorts of solution concepts that economists have proposed. And then in the final part, we're going to talk about bandits and incentives. And here, what we're going to see is that maybe, these ideal settings where there's somebody running an algorithm and they control every aspect of that algorithm, maybe that's not what's happening in the real world. That'll be a problem. Okay. Yeah, take those ones away, and let's make sure these ones are erasable. Okay. Good. So then we're going to talk about what happens maybe in the real world where you don't have full control over every step of the algorithm. You have to interact with other people that have their own incentives in order to run these algorithms, and how does that change the performance of them? Okay, so that's the basic outline of the course. Let me start with some sort of motivation for the machine learning setting. So machine learning is really about making decisions over time using data. So I'm going to discuss three sort of prototypical examples of where you might encounter this sort of problem, and maybe you can, thank you, come up with some of your own as well. I'd love this to be pretty interactive, and so I'll be asking you questions, and I'm very good with uncomfortable silences, so you might want to reply. And so making decisions over time, some examples that I have in mind here, this one that we kind of often hear in machine learning courses is you're the CEO of a weather channel, and each evening you have to put out a weather report. And so what are you going to do? Well, you know, you don't know much about the weather, but you listen to a bunch of experts. A bunch of scientists are going to make some forecasts about the weather. And then you get to pick one and broadcast his or her report. So you pick one and you put it on the TV. Well, then the next morning, something happens. It's sunny or it's not. So the next morning, you observe the weather. And what you would like to do is you're going to see, was your broadcast correct? You get to also see all the other experts, all the other weather forecasters that you didn't choose to broadcast. Were they correct? Would you have been correct if you had followed them instead? So you're gonna see all of that stuff, and you would like to maximize the number of correct forecasts you make. So your payoff here as the algorithm is the number of times that you were correct about the weather. Okay, so this is a decision problem over time. Every day you're making a new decision, which expert to broadcast, and in order to make this decision, you can use data about how they performed in the past. So this is an example of a machine learning problem. I want to now introduce a second example of a machine learning problem, which is maybe on the surface a little more difficult. So now, instead of having a weather channel, you have a movie recommendation site. And each day, a user is going to come, the user is going to come to your customer is going to come to your website, and they watch one movie per night. So they're going to come to your website, and you're going to pick a movie to recommend. And then the user is going to watch the movie or not. So you observe if the user watches the movie. And then your objective is to maximize the number of movies that you recommend that the user watches. So you want to maximize the number of accepted recommendations. And the thing that's harder potentially about this is if I told you to watch Frozen, I don't know, I can see whether you decided to watch Frozen, but I don't know whether if I had instead asked you to watch, say, Agira, the Wrath of God, which is my favorite movie. It's by Werner Herzog. It's much darker than Frozen. I don't know if you would have watched it if I didn't recommend it, right? So I only get to see the feedback that I get, the data that I generate in order to make my online decisions is only the data of the actions that I recommend. I don't get to see the feedback from the actions that I don't recommend. So this seems like a slightly harder thing. And we'll see that, in fact, very similar algorithms can be used to solve both of these problems. Then a final thing that I wanted to suggest as a potential application of this field is penalty kicks. So I've heard you guys all like soccer a lot. So penalty kicks is an example of an online decision problem if you think about it. You are going to have a shootout in some World Cup game, let's say, and you need to decide as the goalie and as the kicker whether to jump left or kick left and jump right or kick right. So each round, you're going to, let's say that you're the kicker, so you decide whether to kick left or right. And then you observe how the goalie responded. And your objective is to maximize the number of goals that you successfully get in. So if you, let's assume that if you kick left and the goalie jumps right, it goes in. If you kick left and the goalie jumps left, it's blocked. And so this is another sort of online decision problem. Every round you're deciding which way to kick. And the complication here is that the goalie is also every round responding to what you've done in the past. So now not only is it, I guess in this instance, the way I've stated it, you have, again, full feedback about what would have happened if you had done something different. But there's a new complication here, which is that the data that is generated could be impacted by your own choices, because if you're always kicking left, eventually the goalie will just always jump left, and so you're always, like, your choices are influencing the outcome. So these are 3 examples of machine learning models, machine learning problems, and what I would like to do first is focus in on this one and come up with a way to an algorithm to use all of this data to generate good forecasts. So I am going to call this the full feedback model. It'd be really nice if I could erase this at some point soon. I can turn it. Wow. Yes. Well, I'm going to need this board again at some point, but I'll turn it. Okay. So we have a full feedback model. This is called full feedback because you get to see in this weather forecasting example what would have happened if you had done any of the other things you could have done. So in the full feedback model, you see all payoffs. Okay, and so I'm going to introduce some notation now. We're going to have a set of actions or experts that we can take. I'll probably use these two terms maybe interchangeably during the full feedback model, because here like an action is listening to one expert versus listening to another expert. When we get here, it's more natural to talk about actions instead of experts, because over here, your action is which movie to recommend. So there's K potential actions or experts. We also are gonna set a time horizon. So you're gonna be doing this for T rounds, and you want to get, you know, a high number of correct forecasts over the course of the year, let's say. Okay, so that's T is the number of rounds that you're doing for this game. And then action or experts, J's payoff in round little t, so I'll index the rounds by little t, is going to be denoted by V for the value that you're receiving of, in time step t of action J. For now, I'm going to assume that these are going to be 0, 1. Your exercises will also assume that for the start. Where is Salvador? Stand up. This is your lovely TA for the afternoon session, Salvador from Mexico. Not Mexico City, but I can't pronounce the name of where you're from, so I'll leave it at that. Yeah, so he'll be leading you through some exercises that will help you dive into the material a little more. And so, okay, so we're gonna assume that the payoffs are either 0 or 1, like the expert was either correct in their forecast or incorrect. Everything I'm telling you will extend to bounded payoffs, and I'm gonna actually use that at one point, but I'm not going to prove things with that. You can look into the textbook if you like. By the way, the first half of lecture is very much based off of a text that is freely available online, and I will, the notes have a link to the textbook, and I'll also mention it at the end, so you can just go there and read up if you like. And also, the notes will be provided to you electronically if they haven't already been. So, okay, so then in round T, your algorithm is going to choose some action or expert JT. So that's the, I guess I'm doing superscripts actually. So this is the action that is selected in round T by the algorithm. And then because we're in the full feedback model, you're gonna learn the payoffs V1T up to VKT. So you learn all the payoffs of every action. And then you're going to obtain, as the algorithm, the payoff of the action that you selected. And so the overall, the payoff of over the course of the T rounds of the algorithm is going to be the sum over T equals 1 to capital T of VJTT. So I haven't mentioned how these payoffs are generated. A lot of the literature on banded algorithms and a lot of the literature actually of deep economic relevance, some of which I'll discuss in the second half, assumes that these are generated stochastically. But for today's lecture, for this morning, I'm going to let these be adversarial. So I'm not going to assume anything about how these are generated. An adversary who's trying to hurt your algorithm as much as possible can choose how to generate these numbers. They could flip coins to generate them, or they could just pick them out of their brain to hurt you. And nonetheless, every guarantee I give you is going to be still hold, even when these are chosen adversarially. So. Yeah.
Is there, could two different actions have a payoff of one?
The question was whether two different actions could have a payoff of one, and yes, it could be that there, if we're predicting the weather, could be that there's two correct experts, that's fine. Other questions? Great. So let me map this just to make sure we have the terminology correctly to a weather forecasting example. So in weather forecasting, we could have two experts. So I spent the last week in Morocco with my lovely friend Jason Hartline, trekking through the Sahara Desert. And I was planning for this trip, and I was like, what do you wear in the desert in January? And it's a desert, so it should be warm, right? It's hot. Deserts are hot. So I thought, okay, I'm gonna pack lots of t-shirts and shorts, and then they gave me this lovely scarf thing on the trek so that I could protect my head from the sun, and I'd be nice and cozy warm. And turns out the desert is not hot in January. The desert is cold in January. So we could have, for each day of our trip, the prediction of what the weather was going to be. So we started on the 13th of January. And we were out there for 4 days. It was beautiful and cold. And the tour guide, or Jason, who is, from Chicago, where the temperatures right now, I think Bo was telling me it's -5 in, Salvador is telling me it's -5 in State College. So that's Fahrenheit, not Celsius. So I don't even know what that is in Celsius, but it's very cold. So these guys, they're all from cold places, and they're like, yeah, it's gonna be hot. And then the tour guide was like, no, it's gonna be cold. You should bring long underwear. And I trust my friend, so I listened to Jason, and I was like, oh, it's gonna be hot, I'm gonna wear shorts on day one. And we flew from Marrakesh to Arequipa and got off the plane, and I actually checked all these temperatures. It was 3 Celsius. And I was shivering. It was very cold. I was very annoyed. But I listened to Jason, so I got a payoff of 0 because I had this inappropriate clothing. So I'm gonna say my payoff was 0 if I was told it was hot and the temperature was less than 4 Celsius. So let's assume this isn't actually true, but it makes the weather forecasting work out. Let's suppose I think that anything under 4 Celsius is actually cold. Okay, so my payoff is gonna be 1 if I'm told it's hot and it's greater than 4 Celsius. Okay, so day 2, Jason, who's from Chicago, says it's hot. The tour guide, who has lots of customers, knows that everybody's always cold. And actually, it turned out to be 5 Celsius. So it wasn't so bad. And maybe I listened to Jason again, so I got a payoff of 1. And then on the 15th, it was again cold. And let's say Jason is always saying hot and the tour guide's always saying cold. And then on the 16th, it was actually really cold. It was -1. But by now I had learned to listen to the tour guide, so I was okay. So the potential, one potential algorithm here could be always listen to Jason. If you know Jason, you will know that Jason thinks this is a very good idea. And if you always listen to Jason in this desert, you're going to get a payoff of 1 because there was one day where I would have been happy to have shorts. Another thing you could do is always listen to the tour guide. And if I always listened to the tour guide, I would have been happy here, not here, happy here, and happy here. So I would have had a payoff of 3. And one thing to notice is that this is the best I could have done in hindsight. If I had just decided I'm going to stick to one expert, as like these algorithms are both just picking an expert and sticking to it for all time, the best in hindsight expert was the tour guide. So the question we want to ask is, can we come up with an algorithm that maybe switches around with between experts, but nonetheless is the best in hindsight? Like it does as close to the best in hindsight expert. So is there a way I could have been like, Jason, you're crazy, I'm gonna follow the tour guide. Oh crap, the tour guide was incorrect, I'm gonna follow Jason. I can flip around, but I want the guarantee that at the end of the trip, I'm doing about as well as the best expert in my choices. Now I'm gonna try and turn this board around. Yes?
Why can't nature just observe what you do and then pick the opposite?
Yeah, so the values that the nature selects needs to be, it can be adaptive to what I've done in the past, but today it doesn't get to see what I've done. Yeah. We can talk about adaptive adversaries that can commit even before I start my trip. We can also talk about, non-adaptive adversaries, or oblivious sometimes, which commit even before I start the trip to the whole sequence of values. We can also talk about adaptive adversaries that get to see what choices I made in the past, but at the beginning of the day, before I make my choice, pick their value, pick the values of each action. And I think all the things I tell you today will apply even to that stronger adversary. Any other questions? Okay, so as I said, the objective that I'm striving for here is to find an algorithm that gets payoff close to best in hindsight. Action. What is best in hindsight? So I'm going to call that opt. And opt is defined to be the max over all possible actions of the total payoff that action would have gotten. Okay, so that's just notationally the best in hindsight expert. And now, what do I mean by close to best in hindsight? I'm going to talk about the regret of an algorithm. So the regret, I'll represent it by RT of alg. So the regret of the algorithm at time t is how much worse is it doing than this best in hindsight action. So this is going to be, by definition, opt, which I told you about up here, minus alg, which I told you about over there. Okay, so equals max over j of the sum over t equals 1 to t vjt minus the sum of what actually happened, which is vjt. That's the thing the algorithm selected. And this is the regret, and we want this to be close, and so we're going to call an algorithm to be, have low regret if this vanishes with t. So we say alg is no regret or has no regret if the per round regret vanishes with t. With the time horizon t. So this would be the limit as t goes to infinity of the regret of the algorithm per round should equal 0. Sorry? No, I'm defining this as a positive quantity. Because opt is, well, I guess it's not, I guess you could be doing better than opt. But, intuitively, opt is stronger than the algorithm, and I want this to vanish. In the previous example, what would be my regret if I listened to Jason? 2. 2, right? 3 minus 1, 2. Good. So we understand what regret is. And now if we played, this trip was only 4 days, but I would have a no regret algorithm if we were just in the desert for a year and then restarted this in 5 years and whatever. Like eventually I should have 0 regret as t goes to infinity. So this definition honestly always bothered me a little bit because these algorithms are going to use t. They're going to use what the time horizon is to decide what choices to make. So you have to fix the time horizon that's an input to the algorithm. And then if you want to run this forever, you have to do sort of tricky things like doubling the time horizon and then restarting and doubling it and restarting. And then you can get this kind of bound, but it feels a little silly anyway. And another thing is this notion of regret is natural because I've assumed that these payoffs were chosen adversarially. In economics, I think it would have been much more natural where they use priors or they always assume things are drawn from distributions. So these would have been drawn from some distributions, and then they might have wanted to, then you could even define what the optimal algorithm is that maybe you have discounted payoffs for future payoffs, and then you want to minimize your discounted reward or maximize your discounted reward. So this is really a very CS approach here. All right, so now let's see if we can try to get to this. How could we get low regret in this full feedback model? Or do you guys have any ideas what you might want to try and do? Yeah? Great. So the suggestion was we see all the past in this model, so we get to know who's doing well. We can look at the past and we're like, wow, tour guide's real smart. Let's maybe try to follow the tour guide. That's a good idea. So let's see if we can make that work. So this algorithm is often called exponential weights. Which I'll abbreviate EW, or sometimes it's called hedge, which I find less intuitive, so I will stick with exponential weights. And what you're going to do is, as you suggested, we're going to identify the best action over time and based on the historical performance, and then we're going to try and follow the best action. And in your exercises, you'll see what happens if you try to do that exactly. It turns out that, and you'll also see this, that if you do anything deterministic like that, like you just look at who's been doing the best so far, you're not going to be able to get low regret. The adversary will be able to fool you. So you're going to have to randomize a little bit. And that's what we're going to do here. So we're going to set a learning rate epsilon. It's an ugly epsilon. And then we're going to let V, capital V, I'm regretting some of my notation choices, of a particular arm J at time t to equal the sum of t prime equals 1 to t of Vj t. So this is how many times that arm, that expert, has been correct in the past, right? Because my payoffs are 0, 1, so this is just the number of times that expert has been correct in the past. And so number rounds where J was right. And now I'm going to, in round T, actually, let me make this to T minus 1 because you don't know what happened on round T in round T, all right? So in round, oh, I guess, never mind. In my notation, I did it the other way, so I'll keep it as it was. So in round T, I'm going to choose J with probability proportional to 1 plus epsilon times V J T minus 1. To the power, yeah. To the power of V minus 1. So 1 plus epsilon to the power of V minus 1. Okay, so I'm going to, in other words, pick, I'll call the probability with which I pick this arm pi. So the probability I pick arm action, I also use arm for action a lot, sorry. The probability I pick this at time t is going to equal 1 plus epsilon to the power, as Bo said, of Vj t minus 1 divided by the sum over all the arms of 1 plus epsilon to the power of Vj t minus 1. Good. So that's the algorithm. Let me just, you'll play with it a little bit more in the exercises, but let me just write down what it's doing in each round in the JSON tour guide setting so that we can see what's going on. So in that setting over there, we can look at the probabilities that we pick the JSON versus tour guide in each setting. And that's going to end up being, so we're going to initialize it with a 1. So we're going to, in the first day, we're going to pick them with equal probability. Okay, so if I set each of these to 1, I'm going to pick each of them with probability 1/2 in day 1. And then in day 2, on day 1, the tour guide was right and Jason was wrong. So Jason is getting an additional factor of 0 because he was not right before. So we get 1 plus epsilon to the 0 times 1 is 1, whereas the tour guide was right, so they get a boost. And now we end up picking the tour guide with slightly more probability. How much more probability? Depends on epsilon. And in your exercises, you'll see that, and also in the proof, we'll see that tuning this epsilon is very important. And this is where I mentioned that the algorithms are using capital T in order to get low regret. That's going to come out in this epsilon. You have to decide how long you have to try and get low regret, and then you're going to decide how big to make this epsilon as a function of that parameter. On day 3, the epsilon is, you can also change it over time, and some machine learning algorithms do that, but we'll use a fixed epsilon. On day 3, you see that on day 2, Jason was correct and the tour guide was wrong, so they each get 1 plus epsilon. On day 4, you see that on day 3, Jason was wrong again and the tour guide was correct. So we get something like this. And so you can see how the algorithm unfolds. Good. So this is just an algorithm. Is it any good? I would like to argue that, in fact, it satisfies that no regret definition on the first board there. So the first theorem that I'm going to use without proof is that the expected reward that this exponential weights algorithm gets is going to look like, it's going to be at least 1 minus epsilon times opt minus 1 over epsilon log k. Okay, this isn't actually that hard to prove. It's just a little technical and messy. If you guys are very advanced in your exercises, we have an optional exercise that leads you through the proof of this statement. And you can also find it in chapter 11 of the book, chapter 5 of the main book I'm using, and there's a second book as well, and you'll find it in chapter 11 of that book. So there's lots of resources online to see the proof of this statement. But I would like to just use it in the interest of time to prove the regret bound. Yeah? Yeah. No, it's, did I erase the definition of? It's just the sum over the rounds of the of the thing that exponential weights picked in expectation. The payoff that the algorithm gets. The payoff that the algorithm gets in expectation. There's a theorem that says it's at least this. And now I want to prove, as a corollary of this theorem, that the expected regret of the exponential weights algorithm is vanishing as t grows. Okay, so in particular, I'll prove the following statement, that the expected regret of exponential weights is going to be at most 2 square root of t log k. Now, this is another thing that's a little annoying, is like most people seem to be writing regret bounds in terms of the total instead of the per round. So the total is not vanishing, right? It grows like root t, but the per round, because we average over all t rounds, is vanishing. So I'm going to adapt this typical statement and look for regrets that are sublinear in t. So that's why I'm writing it like this. Okay, so how do I prove this? So the first thing to notice is that, so I need to prove, the regret has a formula which is opt minus alg, or the exponential weights thing here. The first thing to notice is that opt is at most t, right? Because it could, at best, there's an expert that's always correct. So opt is at most t. And the exponential yeah, okay, so the exponential weights algorithm is going to be, by this theorem, at least opt minus epsilon times opt, which I'll replace with epsilon times t, minus 1 over epsilon log k. Okay, so I just applied the theorem there in that line. And now I have this epsilon, which I get to set. I didn't tell you what it was. I told you we have to care about how we tune it. Now I'm going to decide the tuning. I have these two terms, one which grows with epsilon and one which shrinks with epsilon. So in order to optimize this, I want to set them equal. So I'm going to now specify what I'm setting epsilon to. So I'm going to choose epsilon to equate epsilon t equal 1 over epsilon log t. And to solve that, well, we have an epsilon squared, and then we get a log k over t, so we get epsilon is equal to square root of log k over t. All right? Okay, and then I can just sub this all into the definition of regret. And what I will find is that the expectation of the regret of this exponential weights algorithm, which is opt minus alg, is going to be at most, now I'm going to use the bound I found from the theorem statement on exponential weights, it's going to be at most opt minus opt plus epsilon t plus 1 over epsilon log k. I'm just subbing in this line here. And now these opts cancel, and so this is at most, and now I can sub in the epsilon here. So it's going to be at most twice square root of epsilon is has a t in the denominator, so that's going to be come up here. And that's the theorem statement. Oh, that's much better. Thank you. How do you make that thing see? Does this work?
So I think it's better.
How can you make that thing stand up again?
Yes, yes. Okay, better.
Are you sure you want it unfolded? Withhold it or use your notes?
I just want it like it was before I picked it up. have my hands. Yeah, is this good? Okay, great. So this is cool, right? We got like a sublinear regret for this problem, even when an adversary is trying to fool us all the time, and it doesn't matter, we can still do almost as well as the best expert, which is pretty great. But we're using, in order to decide how to choose between the experts, we're using the performance of both of them in the past, right? And that was very important for the algorithm. Like we needed to like start following the ones that look like they're doing better. But if we had never seen them before, we wouldn't know they were doing better. So we really relied on the fact that we could see what they were doing and how well they were doing, even when we didn't pick them. Yeah? So the question was, how do I choose the epsilon if I don't know the number of rounds, capital T, right? Yeah, so it is true that I'm tuning the epsilon for a particular time horizon. There's a hacky way, I don't know if Bo has better ways to solve this problem, but one hacky way to solve this problem is if you, first of all, there's something called anytime regret. And these are different algorithms that are going to work at any time and have low regret at that time. I'm not going to show you those algorithms, but there are such algorithms in some settings. The other answer is if you don't know the time horizon, you can try to do well over all time by first you solve this problem assuming the time horizon is t equals 2. Then you solve this problem assuming the time horizon is t equals 4. Then you do it again for t equals 8. And every time you're just restarting your algorithm. So first you just run for 2 rounds, and then you erase everything and redo it for 4 rounds, and then you erase everything and redo it for 8 rounds. And so you're like eventually getting to a place where you're gonna have, like, so now if t is infinity, you're going to be doing well in the limit because the exponential sequence is growing and your final thing is dominating.
So Amar is students of the PhD program. So we did the Blackwell approachability also can solve this problem. And you can, for example, play proportional to the regrets as we did. So that's to give him connection with what we did during the course.
Cool. But as I was saying, this is using very much the fact, it's using T, but it's also very much using the fact that we know how well everybody's doing over time. So let's see what we can do if we don't know that. Is the partial feedback model I discussed at the very beginning. So now instead of running a weather forecasting service, you're running a movie recommendation website. You can recommend a movie. You know if your recommendation was, quote, correct, i.e. the user watched it, or incorrect, the user ignored it. But you don't know if you had recommended a different movie, if they would have watched that different movie. So this is the partial feedback model. And it looks very similar to the full feedback model, but I will rewrite it out since we erased that. So you see the payoff of selected action only. That's the difference. As before, you have K actions. You have T rounds. You have action J's payoff in round T is adversarially chosen to be some V JT in 0, 1. And again, this is for simplicity of lecture. This extends to any bounded interval for the rewards. And then in round T, you have the algorithm chooses action JT. Then it learns the payoff VJTT. So this is the difference. Before I said it learns the payoff of every action. Now I'm telling you it only learns the payoff of the one it selected. And then, it obtains that payoff. And then we get the same definition for the reward of the algorithm. It's the sum over t equals 1 to t of VJTT. And as before, we want to find a no regret algorithm with this same definition of regret, but with this more constrained algorithmic design setting. So the algorithm has less power. Can we still obtain that same regret bound? And the real challenge here is that you only learn the payoffs of what you've done. So you could try to exploit the good actions that you've seen in the past, but you might not have seen all the actions. And so you have to force yourself to sometimes give up on this idea that someone recommended of just doing what's been done in the past and worked well. You have to give up on that and do some exploration to learn about things you haven't seen before. So this is the sort of explore-exploit trade-off. You have to explore to learn about other actions versus exploit to milk the actions that you know are good. Okay, so how do we manage to do this explore-exploit? And all we know so far is that we have the algorithm, this exponential weights algorithm, that seems to do well if it knows everything. Is there a way that we could maybe leverage that to do well when we don't know everything? So what do you guys, what might you try, you think? Well, then you can't answer. Yeah?
For a bound amount of steps, we could just sample everyone uniformly and then work on that.
Okay, so one idea, so as you've noticed, the problem is we don't know how well every arm is doing. So maybe we could just sample uniformly or round robin through the arms for the first 10 rounds. Now we have some information about how well every arm is doing. If there's 2 arms, we have 5 rounds of information with such a strategy about each arm. And then we could commit to always following the algorithm that did the best in those first, on those rounds where we observed it. That's what you're suggesting, right? Okay, great. Do we see any potential issues with that? If you were the adversary, not you, if you were the adversary, what would you do to defeat such an algorithm? Yeah, so the suggestion was because we have an adversarial settings of the values, it knows that this is your algorithm, it'll have Jason be right about the weather for the first 10 days and then never again, and have the other guy be wrong about the weather for the first 10 days and then always perfect. So you could try to pick the value of 10 to maybe help with this, but in those 10 days, you're also losing on every round with probability half. So there's not really a way to fix this problem in the adversarial setting. But this is a good idea to try and explore a bit to learn what's doing well. Somebody want to suggest something, a tweak to this idea? Yeah?
Instead of committing to one, just pick the one that continues to give you the highest value.
Instead of what to one?
Not committing to one.
Not, oh.
After some steps, just follow the one that has the best.
So instead of, we're not going to commit to one, we're going to follow whatever has the best. So like, in this adversary you guys suggested to defeat this thing, we're going to see that the one we thought was doing well is doing poorly, and then maybe we'll switch to the other one. Okay, so that's close to what I want. Let's see if we can make this work for us. So we're going to do something like that, and we're going to do it with a reduction to full feedback. So we already know something that works well in full feedback. We don't have full feedback, but maybe we can mimic having full feedback and thereby have the full feedback algorithm tell us how to move around between the experts. So I'm going to sketch the idea here, and then we'll fill in the details. So given some epsilon, that's the learning rate, what we're going to do is in each round T, I'm going to call this exponential weights algorithm that we defined over there, which we know is doing well. And it's going to spit back out to me. Of course, I have to call it with full feedback. I'll tell you how to, I'll mention that in a moment. But let's suppose we've done that in the first T-1 rounds. So now in round T, this guy is going to spit back to me some distribution pi t over the actions. And then I'm going to draw action j from this pi t. Okay, so this is what exponential weights would have done. Then I'm going to choose an action jt. This is what I'm actually going to do. It may be what exponential weights would have done. It may not. We'll have to decide when to follow the recommendation of exponential weights and when not. So this is to be determined, how I'm going to choose JT, but it's going to use this information. And then I am going to observe the payoff. This is from the partial feedback model. I get to observe the payoff of this particular arm that I chose, the particular action that I chose to follow. But I need to, if I want to use exponential weights again in round T+1, I need to give it full feedback, not just feedback about this particular arm. And so in order to do that, I'm going to define some fake payoffs. And for all the actions, not just the one I saw. And I'll have to tell you how I'm going to do that. We'll think about that later. And then I'm going to return the fake payoffs to exponential weights. And thereby, it can tell me again on round T+1 what I should be doing. So this is kind of like the idea. Of course, there's two main unknowns here that are going to dictate whether this works at all. So the first idea to make this thing work out is going to be that instead of, how are we going to define these fake payoffs? We're going to try to find a guess for all the arms payoffs such that in expectation it's right. And so what I want is to use an unbiased estimator of the payoff as the fake payoff. There's a very commonly used unbiased estimator for random variables like this, which is called IPS, inverse propensity scoring. And the idea is that, let's suppose that the alg, I haven't exactly told you how I'm going to choose the action. Let's suppose that the alg chooses the action by sampling from some distribution QT. Okay. Could be pi t. If jt was equal to j, then this qt would be pi t, but I'm going to actually do something a little bit tweaked. But if we assume that the algorithm is sampling from this distribution, then it's going to, then what does that mean? It's going to select jt from qt, and it's going to learn the payoff of that arm, vjt t. And then I'm going to have it do the fake payoffs. It's going to estimate the payoffs for all arms as, let's call it v hat t, is going to be 0 for all the arms except the jth one. And for the jth one, I'll set it to the thing that I observed divided by the probability that I would have selected that arm. Okay, so what's this doing? It's inflating. If I have a very low chance of observing a thing, I'm inflating the value I estimate for it. Okay, if I have a very high chance of observing, like if I'm always picking the same arm, I'm just going to use what I know it is. But if I'm not always picking it, I need to account for the fact that on the times when I'm not picking it, I'm pretending its value is 0 when it really wasn't, probably wasn't, right? So I have to inflate the value a little bit. The second idea is going to be, well, I don't want to never look at a thing, because it could have been, if my adversary knows I never pick arm 1, it's just going to make arm 1 the best thing possible, right? So I need to pick this Q such that I'm definitely picking each action with some bounded positive probability. So I'm going to make sure QT picks each action with positive probability. So in each round, I need to have some chance of picking each action. Now, these two facts together give us the main claim that's going to allow all of this reduction to go through, which is that the expected value of the fake payoffs of each arm, conditional on the Q that I'm picking here, is going to equal the actual value of the arm. So in expectation, conditioning on the Q, I'm correct in the values I'm giving, even though I'm giving 0 for a lot of them. Yeah? Questions? Yeah?
What about if you select randomly one or the other? So Jason or
Tour guide or Jason?
the guide. And then randomly mean, for example, just with the Gaussian. And then you fit the distribution according to results that you have, because you must select a distribution.
So what happens if I select randomly each guide, and then I fit each action, and then I fit the action to I fit what?
Then you have a result, and then you decide which distribution is the best one according to the results that you get.
So you're asking me to try and learn Q.
Because you don't know distribution, so you have to fit it. And how do you fit it? It's because the feedback that you get.
I mean, I am going to be I haven't told you yet how I'm going to pick each action with positive probability. Basically, I'm going to follow this thing and then spread a uniform mass over all the other arms. And you're saying that feels lossy because I could try, like this theorem statement is true for any Q that's bounded. I mean, I need this to be bounded from below because I can't condition on a 0 probability event, but other than that, this will hold for any Q that I pick. And you're saying, why are you picking this? Like, why don't you be smart about the Q? I don't know if that results in improved pounds. I think probably not because I'm getting a root T regret. But yeah, you can play those games. So this claim, I think I'm going to show you the proof because it's very short. The expectation of Vj hat given Qt is going to equal the probability that the selected arm is equal to J. If the selected arm, conditional on the Qt, if the selected arm is equal to J, then I get to observe the V value, and the V hat would set it to this thing. So then it's going to be V Tj over Qj. And if the selected arm was not equal to J, then I'm setting it to 0. Right? So this is the expectation of the fake payoff. And now this thing here is just Qj, the probability that I selected the arm. So this part cancels with this part, and I'm left with Vjt. Okay, so the expected fake payoff is equal to the real payoff. And notice that I'm using the fact that these are positive in this proof. Okay, so So now what I want to show you is that the fake payoffs, so I want to use the fact that this exponential weights algorithm has low regret to claim that this reduction thing is going to have low regret. So the exponential weights algorithm has low regret with respect to these fake payoffs, because like it's guaranteeing me low regret, right, with respect to what the data it has is. The data it has is fake. It's this V hat stuff. So what I wanted to claim now is that even though it's low regret with respect to these fake payoffs, because these fake payoffs are good representations of the true ones, exponential weights with the fake payoffs, it also gets low regret with respect to the true payoffs. So the claim is that any algorithm with these fake payoffs that I've defined for you is going to satisfy that the real regret at any time, actually little t, of the algorithm when it's run on the real payoffs, so this is the algorithm run on the V's, is going to be at most the fake regret, which is the regret that this algorithm has at that time when run on the v-hats. I'm just gonna give you the proof sketch. You can look in the notes or the book for the full proof, but this is gonna hold. It's kind of intuitive that this holds given what we know so far, because the expected performance remains the same because the expected values are the same, okay? And then the fake opt, right? This fake regret has a fake opt in it because it's using the fake rewards. So the next thing we need, so the expected performance is the same between the fake setting and the real setting. And the fake opt, which the regret bound here is leveraging, is at least the real opt. And this follows from, the opt is choosing the max over all arms of the sum of the rewards of the arms. And so to get from fake opt to real opt, we have to do exchange of an expectation operator and a maximization operator, and the inequality turns out to work in the right way. So you can look at the notes to see that proof. I'm gonna skip it in the interest of time. But this claim now allows us to leverage the regret bound for exponential weights that we proved to show that this algorithm here has low regret. So that's going to be the final thing I do before the break. The break's at 10:30, right? Yeah. Okay. So this algorithm, we've now decided how to choose the action. It's, oh, did I skip that? I think I skipped that. Where was that? Right, so we're going to, I mentioned it but briefly, but the way that we're going to do this is we're going to set the QT equal to, so there's going to be some learning rate lambda, let's call it. I guess I'm calling it gamma in the notes. Okay, gamma. And the QT with probability 1 minus gamma, we're going to just do what the exponential weights distribution asked us to do. And with probability gamma over k, where k is the number of actions, with probability gamma, we're going to pick one with probability 1 over k each of the actions. Okay, so this is, I do what exponential weights asked me to do with probability 1 minus gamma, and with that's the sort of exploit probability. And with probability gamma, I explore uniformly. And this is what you were complaining about, right? But this is the Q I'm gonna select. And then I told you how we're gonna do the fake payoffs. That's this thing over here. So this is the learning rate here. You can think about this as I'm exploiting when I'm following exponential weights. I mean, exponential weights then does some other stuff, but you can think about this as I'm exploiting in following exponential weights. Here I'm exploring, because I'm ignoring exponential weights and going around and doing whatever I want. And I'm using exponential weights, and for this reason, because there's 3 things that start with EXP, this algorithm is called EXP3. I'm exploring and exploiting with exponential weights, 3 exp's. So the theorem that I want to prove is that the regret of this thing that I'm calling EXP3 is big O of t to the 2/3 k log k to the 1/3. Do we know big O notation? Okay. So the proof what? Yes, I need to pick the gamma. So in each round t, and I'll do that in the proof, the regret is at most 1 from the random choice. So when I decide to ignore exponential weights, I'm going to incur potentially regret, but that can be at most 1, because in the worst case, the thing I pick has 0 payoff, and the thing exponential weights, or the optimal thing has 1 payoff of 1. And therefore, the expected regret of EXP3 is at most the expected regret of exponential weights plus gamma times t. Right? If I follow exponential weights, I'm getting the regret bound of exponential weights. If I don't, I'm losing at most t in each round. And by this claim here that the fake payoff, the fake regret and the real regret are the same, this is going to be at most the fake regret of exponential weights plus gamma t. I should have picked a Greek letter that I can actually write. And then this is by the bound we have on exponential weights. It's going to be order square root of t log k. I mean, it was 2 square root of t log k. But notice that when I proved to you the exponential weight regret bound, I was doing it in a case where the payoffs were 0 or 1. Here, I'm actually sometimes feeding it high payoffs. They're still bounded because I'm lower bounding this probability with which I select each arm in each round. So when you change your Q, you still have to satisfy that. But it could be higher than 1. And so I need to add in here a term to account for that. That turns out to be k over gamma. And then I have this gamma t. And now I can choose, so now I again optimize gamma to balance these 2 terms. Turns out that to do that, I set them equal, and I choose gamma equal to t to the minus 1/3 k log k to the 1/3. And that's, if you sub it in, it's going to give you the regret bound that you asked for. And so this shows sublinear regret. This is actually not the optimal regret. You could tweak this analysis without changing the algorithm. You can tweak the analysis to actually get a t to the 1/2. I'm not entirely sure how to do that. You can look in the book. But so this algorithm, in fact, gets a regret of t to the 1/2. So that's all I wanted to tell you before the break. After the break, we'll see how all of this relates to economics.
So let's have our second part, starting with Nicole.
Thank you. Yes,
Thank
I forgot to specify the textbooks that are available freely online as PDFs that I'm using for this lecture. So you'll get them in the lecture notes, but I'll write them here as well, so you can all look into it. So the one that I find most useful, because it's succinct, is Introduction to Multi-Armed Bandits. And this is by my colleague at Microsoft, Alex Lifkins. It's based on the lecture notes of a course he taught at UMD. And the other one that you can find online, which is a bit more detailed, is called Bandit Algorithms. And this is by Latimore and Jespej, something like that. Yeah, so those, if you Google those phrases, I'm sure you'll find the PDF of those books. They're great for this basic material that I presented in the first half. And also the first one, Alex's book, is gonna cover a bunch of the material I'm talking about now. Maybe the other one does too, I'm not entirely sure. So good references. Also, Salvador will lead the session, the TA problem solving session. If you have questions about the basic material, I mean, you can find me during lunch, or Salvador would also be happy to cover some of the stuff I covered maybe a little too quickly. He can work through that in the recitation as well. All right, so as I mentioned before in the beginning of the lecture, the second half of this lecture is going to look at the interplay of these machine learning algorithms that we learned about in the first half of the lecture and economics. And so the first thing I'd like to talk about, and I'll spend most of the lecture doing this, is bandits and games. And so I want to think about, we play a lot of games in life, and life is a game, and we're just sort of taking actions and trying to maximize for ourselves, and our actions impact other people's actions. And so this is the kind of thing I have in mind. What if, in order to decide how to act in life, you used one of these machine learning algorithms? What would happen? Would you do well? What would your regret be? This is the kind of thing I want to think about now. And I'm gonna, for most of this, think about this in the context of a zero-sum game. So this is a game like, say, penalty kicks, where there's a winner and a loser. The payoffs are such that the payoff of the winner plus the payoff of the loser sum to zero. Or there could be multiple players, but I'll think about 2 players. So this is a game where the sum of the payoffs of the players sum to 0. That's why it's called zero sum. And I'm gonna focus on this for simplicity. In the final sort of slides or blackboards of this lecture, we'll see some results on non-zero sum games as well. But let's start with a zero-sum game. So in a zero-sum game, I'm going to have a k by k matrix M. This matrix, the entries of this matrix are going to be the payoffs of the players. I'll tell you how. I'm going to have what I'll call the row player, and I'll call the row player alg for now, because I'm going to be talking about the row player using a machine learning algorithm. And this row player's actions are the rows of M. So you have K actions. This doesn't have to be K by K. It could be K by L, but let's just simplify our lives and make it K by K. So the row player gets to pick one row, one of these K rows has K actions, call them 1, 2, 3, right? Like these are the actions that the row player can take. And the column player, similarly, for now, let's call the column player for adversary, has the actions being the columns of the matrix M. And then the payoff of some action profile when the row player picks I and the column player picks J, the payoff is going to be the ijth matrix, the ijth entry of M for the algorithm, which I will from now on write as M of ij. So this is for the row player. And minus mij for the adversary. So, we have our example of our penalty kick game. We have a 2 by 2 matrix. We can think about this row player is the kicker. The column player is maybe the goalie. The row player can choose to kick right or left. And then the column player, the goalie, can choose to jump right or left. And so if the kicker kicks right and the goalie jumps right, the ball doesn't go in, so the payoff to the kicker is 0. And if, I guess maybe it's more natural to say -1 and the payoff to the goalie is 1. If the kicker kicks right and the goalie jumps left, it goes in, they get a 1. And then we can fill out the rest of the matrix 1 and -1. Okay, so this is a zero-sum game. These are the payoffs. And in a repeated zero-sum game, so we're trying to use machine learning to solve these repeated zero-sum games. So in the repeated game, in each round T, we simultaneously choose IT, so the algorithm or the row player chooses IT, and simultaneously the column player chooses the column JT. And then they get payoffs according to the game matrix. So M of IT JT for the algorithm, and minus that for the adversary, and then observe feedback. And this feedback could be, we could be in the partial feedback model or the full feedback model. So it could be that I observe all the entries of the column that I picked as the kicker. So I observe that if I had kicked left, I would have gotten 1, and I kicked right and I got -1. Or it could be partial feedback where I only observe the payoff of what happened. Okay. So we would like to think about the performance of, or the payoff of the players in this game. So let's start with what should happen in a single shot game. So let's ignore the fact that there's many rounds. Just in a single shot of this game, a single instance of this game, what sort of payoffs should we expect the kicker and the goalie to achieve in when they're playing optimally? I'm going to put these back to 0 because otherwise I'll get messed up with my notes. But games have this nice property that as you shift the payoffs and scale them, the equilibria don't change. So that didn't really change much. Okay, so we'll talk about the value of a game. Let's let P and Q be distributions over the rows and columns of M. So P is a distribution over the rows. It's the probability with which the kicker kicks left or right. Q is a distribution over the columns. It's the probability with which the goalie jumps right versus left. Then we can write down the expected payoff of those random strategies. Let's talk about the row player. The column player is just minus the row player. So the expected payoff of the row player is going to be M of P comma Q. And that's P transpose MQ. I'll also, instead of, when I write M of IJ, I mean the P that deterministically selects row I, and the Q that deterministically selects row J, and that's MIJ. So what's the best payoff that the row player can guarantee? Well, I want to define the best payoff the row player can guarantee. They're going to try and pick the way to randomize over the rows that optimizes their worst case payoff. That's what I mean by the best payoff that they can guarantee. And so the best payoff they can guarantee, they want to get as high as possible, pick a distribution P that gets them as high a payoff as possible when the adversary, the column player, is trying to hurt them as much as possible. So the adversary is trying to minimize the payoff that the row player gets. And the question is, how much can the row player guarantee? We're going to call this quantity. This is just some property of the matrix M, right? And we're going to call this quantity V star. And define it to be the mini-max, or I guess it'd be better to call it the maxi-min value of the game. And because of how I've set this up, we know that the row player can guarantee himself a payoff of V star by playing the P that achieves this maximum. So what is P star for the penalty kick game? Yeah? 1/2, yeah, so I put 1/2 weight on each row. With probability half, I jump left. With probability half, I jump right. What's gonna happen if with that P star? I would get, so the suggestion was in the example, we can set P star equal to half. Then I'm gonna get a value V, which is equal to P times 1 minus Q. If I kick left and the goalie jumps right, plus 1 minus P times Q. And then if the P's are 1/2, the Q's will cancel, and I will get a value of 1/2. And so by playing half-half, I get a value of 1/2 in expectation no matter what the opponent does. And the claim is that there's no other distribution I could have picked that would have gotten me a higher guarantee. I can't guarantee myself more than 1/2. And I think this is very intuitive for this penalty kick game, but to argue this would require a proof, and there are many proofs of it, but we'll see one here. And the question is like, how could you have known that as the goalie? You're facing this game, or as the kicker, you're facing this game, and you do some calculation in your head and you decide you should jump left with probability half and kick right with probability half. How did you find that? There's several ways to calculate this. You could write down a linear program, and this is all maybe like questionable thing to expect players to do in the real world in a game. And maybe a more natural thing to do would be to do something like exponential weights, right? It's not, we define this algorithm and it has this learning parameter and everything, and so it might feel a little unnatural to run exactly exponential weights, but I would argue that people do something like this in real life. They think, they look at what's happened based on what they've done in the past, and they maybe try to do things that worked out well for them in the past. And every once in a while, they wake up and feeling adventurous and they do something totally different and see what happens, right? It's a very natural behavioral pattern based on real data that you input as a human. And so I would like to think about these algorithms we discussed in the first half as a protocol for how people behave in the real world and see what would come out of it. Would they end up playing this P-star strategy? Yeah? Yeah?
Why in the first example, the prediction, the previous one about the guide and so on, the weather forecast, the prediction cannot be influenced by the skills of the people, in the sense that the weather is independent on the action of the people. In this case, it's not.
Yes. So the comment was that in what I've done so far in the first half of the lecture, the adversary or nature was picking something like kind of independent of what I do, especially with an oblivious adversary. Whereas here, we're playing a game with each other. So maybe based on how I act, the goalie might change what they do. And that's definitely true. And so these algorithms we did in the last round aren't really taking that into account. Are they nonetheless going to work out well for us in the long run? And we'll see that they will. But yeah, so that it is maybe a little surprising at first glance that this is going to work for us. Okay, so this is like for a single shot game, intuitively, what I would like to guarantee myself is this V star, and that's the best thing I can for sure guarantee myself. And we saw that, like, you know, we calculated what P star would be for the penalty kick. But what about in a repeated game, which is the setting of interest in the first half of this lecture? Can we have a performance guarantee for a repeated game. And what I'd like to argue is that the payoff of the row player using some algorithm to decide how to act based on the data from the past is at least T V star, this performance in each round in the single shot game, minus the regret guarantee of the algorithm. So by doing this very natural thing of kind of doing what worked well for you in the past and sometimes doing random stuff, you can guarantee that you're going to do almost as well and asymptotically exactly as well in each round as you could do in the single shot game. And this is coming from the fact that this algorithm has a good regret guarantee. So let's recall from the first half of the lecture how we defined regret. We said the regret of the algorithm is defined to be opt minus alg. I'm going to get sloppy about taking expectations, so you can just, in your head, think that all of these quantities are an expectation. And what do we know about opt? So opt is, by definition, the max column that the opponent could have picked of the sum, the row that, the maximum over the rows that I could have picked of the sum over the time steps of m of I j t. So it depends on what the opponent picked in that time step, right? And this is at least the sum over t equals 1 to t of m of p star jt. Why? Because p star is guaranteeing me the best against any q. And so then I can get like that this is basically averaging over this distribution, and so that's going to be t times v star. Okay? So this gives me the fact that in this bound, I'm getting, now I just rearrange these terms. So alg is equal to opt minus the regret, and opt I've just shown you is at least t star, and so I get the bound in the theorem statement. No? Okay, so this is saying that I can guarantee myself v star as the algorithm. What about the adversary? What if I have the adversary, here I didn't assume anything about the adversary, and I can guarantee myself something close to v star in each round of this repeated game. What if the adversary, maybe I could do much better. We didn't really talk about that. What about the adversary? What if the adversary isn't some arbitrary adversary, but is also another human being who is also using this sort of heuristic of behavior where they're learning from the past? So maybe the adversary is also using a regret minimizing algorithm, right? This seems like a natural kind of setup. You have just two people playing a game together. They're both going to be using regret minimizing algorithms. So what if we had a regret minimizing adversary? What would the adversary be getting? Would they also be getting something close to, what they could guarantee themselves in a single shot of the game? So first, we want to repeat this exercise for the column player. We've done this for the row player. We're going to do it for the column player. It's going to be pretty much exactly the same, but let me write it down so that we can see what's going on. There's going to be one slight twist. The twist is that what the column player can guarantee himself is they're trying to minimize, not to maximize. So instead of having the max of the min of this thing, we're going to have the min of the max of that thing. So we'll call it the mini-max value. And you know, ex ante, you could imagine it could be different. There's not any obvious reason, for me at least, that this should be equal to V star. It'll turn out to be true. But like, let's call this V double star. So the mini-max value is going to be the min over Q of the max over P of M of PQ. So this is the best that the adversary can guarantee himself. His payoffs minus the outcome, so he's trying to minimize the outcome. So the best he can guarantee himself, no matter what the other guy is doing, of M of PQ. And we can call Q star the argmax of this thing, argmin of this thing. And similar to this, the row player, we can show that the column player payoff is at least minus TV star minus RT of the algorithm that the regret of the algorithm that the adversary is using to pick the columns. The proof is basically the same. And so now what we've seen is that each player can guarantee themselves a payoff that's close to what they would get, you know, a per round payoff that's close to what they could guarantee themselves in a single shot of the game. This guy can, in a single shot of this game, we said the best that he could guarantee himself is V star. And in using this algorithm, no matter what the kicker is doing, no matter what the adversary is doing, even though the adversary might be reacting to him, I mean, this is really leveraging the fact that we had a adversarial setting in part one of the lectures, right? So no matter what the adversary is doing, it could be reacting to me, I can guarantee, from part one, I'm guaranteeing myself this regret. And so per round, because this regret vanishes if I'm using a no regret algorithm, I'm getting V star per round. Okay, so in answer to your question, this is because in the first part of the lecture, we had an adversary that could adapt to what I'm doing each round, and I still can guarantee myself low regret with respect to what they chose to do. And so I'm getting a guarantee of V star per round as the algorithm, as the row player. Similarly, the column player is getting a guarantee of V double star per round, which is the best that they could guarantee themselves. Well, I guess minus V double star because of the zero sumness of the game. But this is the best that they could guarantee themselves in a single shot of the game. But these two things could potentially be different. So what happens when these two things are playing against each other? What kind of outcome are we getting in this game? And to see that, there's this very famous theorem in math called the mini-max theorem, which says the maxi-min value equals the mini-max value. So that's V star, which was the max over P of the min over Q of M of PQ is equal to V double star, which was the min over Q of the max over P of M of PQ. So from now on, I can just refer to V star. That's the value of the game. It's the value that the row player can guarantee minus V star is the value the column player can guarantee. And like this is a tremendously amazing, awesome theorem. It follows from a variety of different proofs, including probably the most common one, I think, is using a linear programming duality, which you might have studied in your courses. But very interestingly, for me at least, you can also prove this theorem using the existence of no regret algorithms. And you'll see that in the recitation section. So we've designed an exercise for you that will, it's not very hard. It's using the proofs that we've seen so far, and you'll be able to work through it and convince yourself that these two things are the same because no regret algorithms exist. So, but for the lecture, what I'd like to do instead is explore a corollary of the Minimax theorem, which is that these mixed strategies form a Nash equilibrium of the single shot game. So what is a Nash equilibrium? It's a pair of distributions for each player over the set of actions available to them, such that the expected payoff of the player is optimized by the distribution that they selected, conditional on the distributions that the others selected. In other words, everybody's playing a best response to everybody else. And so the proof of why this is a Nash equilibrium, these particular, so now I've specified the distributions that you're gonna use. You're gonna use the distributions that guarantee you your payoff V star in this zero-sum game. Why is that gonna be a Nash equilibrium? Let's look at, let's first show that Q star. So I wanna show Q star, for example, is a best response for the column player. And it'll be similar for the row player. So in order to see that, well, P star is going to guarantee the row player at least V star for any choice of the column player. That means that the payoff of the matrix for any Q that the column player picks is at least V star. And so the column player is trying to minimize this. They're trying to pick a Q to minimize this. And by this theorem, Q star achieves that minimum. I mean, Q star is defined to achieve V double star, and by the theorem, it therefore also achieves V star. And so the Q star must have been a best response to this P star of the row player, right? And then similarly, you could go through the same set of arguments for the row player and see that P star is also a best response to Q star. So they're simultaneously best responses to each other, and therefore they form a Nash equilibrium of this game M. And so the Nash equilibrium, for example, of the penalty kick game is for each player to flip a coin and choose each action with equal probability. So this is a, Nash equilibrium of this zero-sum game. It's going to be something you can calculate, but again, we don't want to assume that people are calculating this. You can use linear programming to calculate this, for example, but it seems unnatural that these players on the field are going to calculate this. What if they just use these no regret algorithms? Are they going to end up at a Nash equilibrium? If they just every day in these penalty shootouts, right? You run a no regret algorithm to decide how to kick and how to jump. Will you end up at this Nash equilibrium? And so what we'll see now is that these no regret algorithms in fact approximate a Nash equilibrium. I guess I've been trying to emphasize this, but let me say it again, that Nash equilibrium is kind of the solution concept that economics would introduce, and later we'll see correlated equilibrium, and of course correlated equilibrium as solution concepts from economics. But these solution concepts are kind of like properties that once you see it, it's there, right? But it's not clear how you reach it. And so what I really like about the material that I'm presenting today is that these algorithms are arguing about ways that people could actually behave. Like this is a very natural behavioral assumption after we reach it, then nobody wants to move away. But how do we get to it? And these no regret algorithms get us here in zero-sum games. So that's what I really like about these theories. Okay, so let's see why the no regret algorithm is going to approximate these Nash equilibria. So the theorem that we would like to prove is that the average play, so these no regret algorithms are going to tell me in each round whether to jump left or right, whether to kick left or right. The theorem is that the average play, if I average over what I've done over all these rounds, let's call that P hat, Q hat. These are the empirical distributions of what happened, what was selected. These empirical distributions are going to converge to an approximate Nash equilibrium. In what sense? So what is an epsilon t approximate Nash equilibrium? It's going to be the P hat, Q hat satisfy that there are approximate best responses. So P hat is at least V star minus epsilon t. So P hat is, Q is an approximate best response to P hat. And Q hat is at most V star minus epsilon t for all P. P hat is the empirical, so if you jumped left the first 3 times and then jumped right the 4th time. This epsilon will depend on the time horizon. Yes, it's the empirical, so yes, yes. I mean, I'm dividing it by t, right? So, yes, yeah. I'm stating this guarantee at time capital T, so I didn't feel the need to write the t in there. Yeah. Yeah, yeah, yes. Good. So what is this epsilon t, since you mentioned it? It's going to come from the regret guarantee, obviously, and it's going to be 1 over t times the regret of the algorithm plus the regret of the adversary. And so this is going to converge to 0 if these are no regret algorithms as the time horizon increases. Good, so let's talk about why this is true. Let's first look at the row player and try to think about the algorithm that the row player is using and use the fact that it has low regret to show that the row player is approximately best responding to the column player. So what do we know about this row player's algorithm? From the definition of regret, we know that the algorithm plus the regret of the algorithm is equal to the opt, in the optimal in hindsight choice of the row player. Like, notice here that I'm just rewriting the definition of regret. Regret was opt minus alg. I moved alg over here, right? Okay, so this is going to, well, by definition of opt, it's the max over the choices of the row player of the sum of t equals 1 to t of the payoff if they had just stuck to that one action the whole time. This is the definition of opt. This is going to be there's t time steps, so we can think about this as just the empirical distribution of each one of these. I can collect them all together and divide by t, and I'll get the empirical distribution of the column player here. So this is t times the max over I of m of I comma q. Q hat. Yes. And this is well, okay, so this is the best that the column player, that the row player could do if they were picking a specific row. So if they pick a distribution, it's the same. And now if they pick the best distribution, it can, this is the best distribution against the worst case Q. And so if I'm insisting on using the distribution that's best against the worst case Q, I might not be exploiting Q hat appropriately, so I might lose something. So I get P star Q hat here. And then that's going to be, if I ask the adversary to try and hurt me as much as possible, it's going to be only worse. And by the definition of T star, This is Q star, P star. This is T times the max over P of the min over Q of M of PQ. And this is T V star. Okay, so we have that the algorithm plus this is at least this quantity, and so the payoff of the algorithm is at least TV star minus the regret of the algorithm. So we're getting close to this statement that we want. We need to, of course, also use the column player. And so the column player, their payoff is, because of the zero sum, it's minus what their algorithm is getting. And so this is going to satisfy a similar inequality, which I won't prove for you, but I'll use it, so I'm going to write it down. So it satisfies that the adversary's algorithm minus its regret is, so now this is going to equal T min over Q of M of P hat Q, which is at most T of V star. Okay, so this statement and this statement are basically the same. I've just switched whether I'm using the row or the column player, and so we can get a similar inequality. And then we want to combine these two, so we can say that I'm going to use this first. So I say that T V star minus the regret of the algorithm is at most the algorithm. That's what this first stuff proved, right? So this is at most algorithm, which is equal to the adversary's payoff. So this is using the minimax theorem. This is using the zero sumness of the game, right? So because the game is zero sum, this has to hold. This is going to be at most, by this set of inequalities, the T V star plus the regret bound of the adversary's algorithm. And so this implies that these two payoffs are within or approximating V star as the time horizon grows. And you can also see that it's this epsilon that I claimed is the right epsilon from here. Okay, so this was maybe a little deep. Let's go up a level. This was like a bit technical, but I think it's pretty straightforward, and it's laid out very, step by step in the textbook that I mentioned over there by Slifkins. But this is all about zero-sum games, which is a lot of games. But of course, there's a lot of interesting games that are non-zero-sum. And so how does this all extend? So what we've learned so far is that in a zero-sum game, if everybody's doing this very natural, like regret minimization type strategy, we're going to end up approximating the Nash equilibrium of the zero-sum game over time. And the rate at which we do that will be related to the rate of the regret algorithms. So what happens if the game is not zero-sum? Can we guarantee ourselves anything? And what does that look like? Okay, what is a non-zero-sum game? So I'm going to introduce some more notation. As before, I have a k by k matrix M, but now the entries of M are in our vectors of length 2 if I have 2 players. Again, we have the row player whose actions are rows. And we have, again, the column player whose actions are columns. And now the payoff, I'll call it M sub R of ij to the row player is the first entry in this vector of length 2. And we have M sub C of ij is the payoff to the column player. So just to show you how we often write this, we could write this, I'm going to introduce a sort of coordination game. We have 3 activities that we can do in Morocco. And only 3. This is me. This is Jason. We can go surfing. We can go hiking. And we can teach lectures.
You can do lectures by surfing at the same time as hiking.
Well, these are all in 3 very different locations, so I'm not sure that would work out so well. So Jason really likes surfing, and I'm okay with it. And we like being together. So, I get a payoff of 1 from surfing if Jason also surfs. But if I go surfing and Jason went hiking, I'm going to be really annoyed. So I'm going to pay off of -1, and Jason also is going to be really annoyed. He's going to get a payoff of -1. And if I go surfing and Jason lectures, let's say the payoffs are 0 for each of us. Similarly, I really like hiking, and Jason is willing to be dragged out hiking if I'm there. So he's going to get a payoff of 1 when we go hiking. I'm going to get a payoff of 2. If I hike and he surfs, we get payoffs of -1, and let's put 0, 0 here as well. And then if we both lecture, we're okay with it, but we're just kind of here looking at each other like, why aren't we surfing right now? And so let's suppose that we get payoffs of -1 from lecturing. So this is an example of this notation here. You can see the first entry here is the payoff to the row player. The second entry here is the payoff to the column player. Good.
You can have doing research.
Writing papers. Yeah. Well, I needed something with negative payoffs for a point I want to make later. Okay, so what are the equilibria of this zero-sum game? Non-zero-sum game, thank you. A Nash equilibrium is by definition a distribution PQ such that the expectation when the action I is drawn from P and the action J is drawn from Q independently, that the payoff to the row player of that, the expected payoff to the row player of that action, those pairs of actions, is at least anything else that the row player might have chosen. So I guess let me put it on here. Okay, and similarly for the column players. This is, I'm best responding to the distribution that you're doing. This is the same definition we had in zero-sum games. I'm just writing it out again so you see the notation here. I have to let you know which player I'm talking about, right? Okay, so that's a Nash equilibrium. And I'm not gonna show you this, but these algorithms fail to converge to that Nash equilibrium. Even though in zero-sum games, they converge, we proved they're guaranteed to converge to a Nash equilibrium if we play over enough rounds. In non-zero-sum games, no-regret algorithms might not converge to the Nash equilibrium. However, they will have some kind of guarantee. They're going to converge to something that we call a coarse-correlated equilibrium. So what is a coarse-correlated equilibrium, which I'll often call, just abbreviate CCE? That's going to be a distribution over cells of the matrix. So a distribution over action profiles such that the expectation, so here I was drawing each action independently from the distribution of the row player and the distribution of the column player. In a correlated equilibrium or a coarse correlated equilibrium, I want to draw the action profile in a correlated way. So I'm going to ask that I and J are drawn in a correlated way from this distribution delta. This is a distribution over pairs now of rows and columns. And what is going to be the payoff if the action profile is according to the distribution? It's going to be the expectation of that entry of the matrix for the row player, similarly for the column player. This delta is a coarse correlated equilibrium if this row player doesn't want to deviate to any other action when they know that the distribution is being drawn according to this delta. So when they know the distribution is being drawn according to the delta, they know kind of the distribution over the play of their opponent. Would they want to deviate? So they might want to, we want to say that they don't want to deviate. It means that this must hold for all I naught. So this is like notationally maybe a bit intense, but what's it mean? It means like there's some coordinator who's picking one of the cells of these matrix according to some distribution delta and is gonna send a car to pick me up and pick Jason up and drive us to the beach, to the desert, or to the university, right? And I know the probability with which the car is going to the beach, the desert, or the university. Do I want to get in the car? Or would I rather like decide by myself where to go and find my own transit there, right? And just show up there. So if I want to get in the car, knowing that it has some probability of going to each of these destinations and that Jason is also in the car, then, and then Jason also wants to get in the car, then that would be a coarse correlated equilibrium. Does this make sense? I think this is a slightly confusing concept maybe when you first see it because it some sense allows some kind of commitment power that we're both going to get in the car and we can't get out again if we choose to get in the car. And this is saying we both want to get in the car, knowing the probability with which it goes to each destination. Okay, so what's the coarse correlated, do they exist? We'll see that they exist because we'll see that no regret algorithms converge to them. What is the coarse correlated equilibrium here? We can I'll write the probability with which each cell is selected here. Surf, hike, lecture, surf, hike, lecture. a course correlated equilibrium is that the car goes 1/3 of the time to each destination, and the car is never sending us to separate destinations. Okay, it's gonna it guarantees that we're gonna be together, and it can tell us 1/3 of the time I'm gonna be in the beach, 1/3 of the time I'm gonna be in the desert, 1/3 of the time I'm gonna be lecturing. I claim that this is a course correlated equilibrium. This is a sort of silly one because it's forcing us to get negative payoffs 1/3 of the time, but it's coordinating us in a way that we wouldn't want to deviate anyway. So maybe the government of Morocco likes this payoff matrix for us because they have their own objective or something. So why is this a course correlated equilibrium? Let's look at the row player and see that this inequality is satisfied for the row player. So if they follow the recommendation with probability 1/3, the row player ends up surfing and they get a payoff of 1. With probability 1/3, they end up hiking and get a payoff of 2. And with probability 1/3, they end up lecturing and get a payoff of -1. And so this is 1 minus 1/3 is 2/3. Now, could they deviate and do better knowing that this is where the car is going? This is the distribution of where the car is going. If they're going to deviate, the row player, I argue that the only deviation we have to check is hike, but you could check them all separately if you want. But hike is where the row player has the best chance of doing well. So what happens if the row player deviates to hike? If the row player chooses to hike instead of getting in the car, then the payoff is going to be, well, Jason is still going to end up in each of these places, in each of these destinations with probability 1/3, right? The car is going to each of these with probability 1/3. So if I just deviate and go to the desert with probability 1/3, he doesn't come along, and I get a payoff of -1. With probability 1/3, he's there, and I get a payoff of 1/2. And with probability 1/3, he's lecturing, and
The second one, 2 times 1/3 is 2/3.
yes.
Minus 1/3, 2/3, 0/3.
Yes. You're telling me that the end is 0.
No, 1/3.
1/3. Yes. Right, but so with probability 1/3, this is the cell that realizes probability 1/3. This is the cell that realizes, and with probability 1/3, this is the cell that realizes. So this deviation did not improve my payoff. And you can check the others if you want, although they're going to be even less than that one. And so that this must be a course correlated equilibrium because we're both happy to get in the car. Okay, so is there a course correlated equilibrium? What does it look like? How can we find it? The theorem is that these no regret algorithms are going to converge to a course correlated equilibrium in non-zero sum games. By the way, how do course correlated equilibria relate to Nash equilibria? It's a subset. Why?
What is the subset?
Nash equilibrium.
Why? Good. So Nash equilibrium is a subset of course correlated equilibria because I could have defined a distribution delta, which is to select independently from P and Q. The Nash equilibrium says you don't want to deviate from that, so it works. The other direction is not true. Huh?
Like this example shows.
Yeah, I chose this example to demonstrate a bunch of things, but so here the Nash equilibrium is either we do this or we do this or we mix. Anyway, okay, so I want to now argue that we.
Who never did game theory before? Some people never did game theory.
Okay, yeah. I hope so. So what happens with rivet minimizing players? Playing a non-zero sum game repeatedly. The theorem is that no regret play converges to a course correlated equilibrium. You may be annoyed that I have this word course here. I'll explain why later. Okay, so the proof, let's let delta be the empirical distribution of play. When I say no regret play converges to a course correlated equilibrium, I mean that this delta is going to be a course correlated equilibrium. The empirical distribution of play, just to make sure we're all on the same page, I mean like if you over the T rounds played this a third of the time and this a third of the time and this a third of the time, like, I mean, sorry, this a third of the time, this a third of the time, and this a third of the time. So your algorithms happen to like coordinate somehow to play this, 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 each a third of the time, then this delta is the one I mentioned here. So what do we know about this delta? So this is just, let's take the expectation away and just write it out so that we don't have to worry about that. So we have T 1 to T of MR of IT JT minus 1 over T times alg. I'm regretting the fact that my board is shorter than I'd hoped. Well, anyway. So this is 1 over T I think I'm going to skip. I'm supposed to end at 45 minutes from now, right?
We end in
20 minutes from now.
20 minutes.
Okay, I'm going to skip this proof. I'm sorry. It's in the notes. It's just like working through the algebra. I just want to maybe keep this a little higher level since we're all pretty tired right now. At least I am. So this no regret play converges to a course correlated equilibrium is going to come out of the fact, like it did for the zero-sum game, that I'm guaranteeing myself a good outcome even with respect to an adversary, and you can leverage that to get a theorem like this. And I'll refer you to the notes for that because I want to talk about 2 more high-level things. The first high-level thing is, so I'm skipping a bunch of stuff. Yeah.
Is the reverse also true? Is the course correlated equilibrium, or every correlated equilibrium in every game can be reached by some non-regret algorithms played by players? Or is there a subclass of course correlated equilibrium that we should be looking at?
I don't know the answer to that question.
Ask that question in a nice way.
Because if you have your algorithms like guess a correlated equilibrium at the start, If you have your algorithms guess a correlated equilibrium, just start there. But then if it's not a best response, then maybe do exponential weights. Then you can reach any correlated equilibrium because the algorithm that guesses it starts there. But if you were to look at a restricted family of algorithms, then you'll get a subset of, of course, correlated equilibrium.
But doesn't Blackwell approachability say I can get to any point in the polytope?
Can I also give my?
I think I should close mine probably, or move over here.
Yeah, close yours. Can you close your microphone?
It's closed. I think it's my mic.
Yeah, so just a remark, this is the set of correlated equilibria. You don't converge to a point. Remark one. Remark two, in some class of games, if all players are using a non-regret algorithm, for example, potential games, they converge to a Nash equilibrium. So we will not necessarily converge to the set of correlated equilibria. You will not reach all of them in this game. Yes? So.
The question that was raised before. So, for example, how can we go to that specific correlated strategy if at every iteration players play up like some mixed strategies?
You're saying, like, I mean, if we both have a high probability of surf in a specific round, then the surf profile is going to have a high weight.
I just don't see how that specific correlation could be reached if players keep playing mixed strategies.
Yeah, I understand the question.
It's very unstable.
It does sound confusing. I agree. Like we have to somehow coordinate the rounds on which we're playing surf, right? So it has to be like that we exploit the surf action on the same rounds, and then we learn to like on different rounds also an equal number of time exploit the hike action. So yeah. I'm not converging to a specific mixed distribution, right? Like I can change the distribution I'm playing every round. Yeah?
So let's move perhaps. So in some games, you may converge to a pure equilibrium, for example, even if you are mixing. Imagine that you have a strategy that is strictly dominating all the others, all the players have this. At the end, you will learn this strategy, even if you are mixing. So the fact that you can converge to a corner, it might happen, okay? But for this example, probably this will be difficult. In this example, it looks like unstable to reach this one, in my opinion. So, yeah.
Okay, so just another high-level comment I want to make about this non-zero sum game regret algorithms before I mention a few other things and then we break, is that I told you, like, this is the definition of a coarse correlated equilibrium. Why did I say coarse? Because when I asked if I could deviate and gain, I didn't allow myself to know what the recommendation was. So it wasn't like the taxi driver showed up and said, by the way, I'm going to the university, do you want to get in? If I got to know where the taxi driver was going, then maybe I would want to deviate, right? So a correlated equilibrium says that even if I know where the car is going, I don't want to deviate. So I want to say that this is bigger than this, even if I condition on the recommendation. It's kind of, what did I choose for notation here? Okay. So is this a correlated equilibrium? Why not? So yeah, so if I knew that this car was going to the university, I would get out and go to the beach. So this correlated equilibrium is actually a more famous notion, I think, of equilibria. This was defined by Aumann, and if you ask him, he'll say it's way more natural than Nash equilibrium even. And so for a correlated equilibrium, it would be nice to be able to reach a correlated equilibrium with no regret algorithms. It's not true that the no regret algorithms I've defined for you reach these correlated equilibria. But what is true is that a sort of more refined notion of regret, if we play algorithms that have what we call no swap regret, then we do converge to a correlated equilibrium. So in the no regret algorithms, we're saying we want to do as well as the best action in hindsight. Swap regret says, well, maybe every time you did this thing, you should have instead done this other thing. But you don't have to always replace going to the beach with going surfing. You don't always have to replace everything with going surfing. You can just replace, say, lecturing with going surfing. Okay, and so you look back at the past, you say, do I have low swap regret? I have low swap regret. If there's no way to swap out every time I did lecturing, instead do surfing, and like what would the gain be? So this kind of notion, this like per action notion, if you like, is a different type of regret. There are algorithms with low internal regret of this notion. Then they will converge to a correlated equilibrium when we play them with non-zero sum games. So that's one other thing I wanted to mention. I have a bunch of references here for why these types of things are interesting. So these are specific research papers. You'll find them in the notes when they get emailed to you. These kinds of theories that we've been talking about are really impactful right now for research problems for a variety of reasons. One is that we are thinking a lot at Microsoft, for example, about how to set up automated systems, or like, we use AI for everything these days. What happens when we use learning algorithms to act on our behalf? In Microsoft, one place that we care about this a lot is in the ad auctions. So in the ad auctions, by the very nature of the ad auctions, we absolutely need to have algorithms bidding on the behalf of advertisers. These are the auctions that display ads on your search results. And so how does the fact that we're implementing algorithms to bid on behalf of the advertisers impact the outcomes of these auctions? There's a really great line of research in this area. One of the kind of seminal papers is Blasero and Gur, Learning in Repeated Auctions with Budgets. And it leverages this kind of technology to say that if these auto bidders, as we call them, are implemented with no regret algorithms, then they have good guarantees in terms of the prices that people end up paying. Another area of research that I think is very relevant is the idea that if you assume people are using these algorithms, how can you potentially manipulate them? Or, and if you also use these algorithms, are we going to learn to collude? So this, Jason has a nice paper in this area called The Regulation of Algorithmic Collusion. If, say, a bunch of price setters are using these kinds of algorithms to decide how to set their prices, what kind of prices are we going to end up with? And is that illegal? So in the United States, you're not allowed to call up your competitor and say, hey, we'd both be better off if we had high prices. Why don't we keep our prices high? And let's just not undercut each other. That's collusion, that's illegal. Are these algorithms going to learn to collude? Is that something we should regulate? You're gonna play around with this in an exercise after the break. Yes. And I guess another setting is kind of like this idea of mechanism design for agents that are no regret agents. Like, can you set up a way to sell stuff to maybe exploit those players that are using no regret algorithms? And is there a way that they can safeguard themselves by implementing specific ones of these? So these are kind of some current research streams that I think are very interesting and you guys can all work on. In the last few minutes, I'm gonna maybe stop writing, but I just wanna tell you about what else I had planned to tell you about. The other thing I think is interesting, this is about using bandits to play games, using these algorithms to play games. But I also mentioned in the beginning of the lecture, what happens if we can't implement these algorithms directly because we don't have full control? Maybe the algorithms are being jointly implemented by society as a whole, and in this decentralized world, can we still get good outcomes? This is the subject of incentivized exploration. So in incentivized exploration, the idea is that there's a bunch of actions that can be taken, but I, as the algorithm designer, can't dictate which actions to try. The actions are chosen by some independent people, and they are gonna pick things that they're incentivized to try. So you could imagine, for example, in the movie recommendation site, I have 5 movies. I'm trying to learn what's the best movie. I'd really like you to watch the one I'm not sure about so I can learn and make a better recommendation for tomorrow's customer. But you don't want to watch the one I'm not sure about because there's this other one that has really great star rating. So you want to go watch this other one. How can I convince you to watch the one that I want you to watch, even though that's not in your best interest? And the way that potentially I can do this, and notice I have to get you to explore in order to get good regret guarantees, as we saw with the first half of the lecture. So in order to get you to do this, what I'm gonna, the thing I can use is the fact that I know the past as the platform. I know the star ratings of all the movies that people have issued in the past, but you do not know that unless I tell it to you. So can I leverage this information asymmetry to convince you to do a thing that you weren't gonna do anyway? It's a way of incentivizing actions without payments or anything. You know that I have some information that you don't. And so if I sometimes use that in your benefit, you'll listen to me. And there's a limit to how much I can do that, because if I do it too much, you're gonna stop listening to me. And so in the exercises, you'll work through this concept of like, how much can I convince you to explore without, like when I want you to explore by using this kind of information asymmetry. I think I'll stop there. And there's a few more things in the notes, and there's stuff worked out in the notes, so you can look over it yourself, but thanks for listening.